and I have given you LC oscillator general topology, and we put 3 admittances in a T network, pi network, and then by choice of this Y1, Y2, Y3, we have different types of oscillators, Colpitts, Hartley, and so on and so forth. Basically, the structures are either Colpitts or Hartley. In Colpitts, you have 2 capacitors and 1 inductor. In the Hartley, you have 2 inductors and 1 capacitor. Sometimes the 2 inductors are realized in practice by a mutually coupled coil, but that is not an important issue. I mean, you can do simply 2 inductors or 1 inductor with a mutual coupling. And but there are 2 other variants of Colpitts oscillator, which is the Clap oscillator and the Pierce oscillator, right. These are basically Colpitts oscillators. In Colpitts, if you remember, we have an inductor in the feedback path and 2 capacitors, right. Now, if I replace this inductor in Clap, what they do is they replace this by a series tuned circuit. Now, we will see why it is a better way of doing Colpitts and why this Clap became important structure is the following. If you really see the admittance of this, I mean reactance of this, there is 0, which is the resonant frequency of the series circuit, and if this is omega and if this is x omega, then the x will be like this, because at very low frequencies this is effectively a capacitance and very high frequencies is effectively an inductor, and in between it changes the from capacitive reactance to inductive reactance while it goes through 0. So, this is the way the x omega varies with respect to omega. We are looking for an inductor here. So, obviously, the range of operation of this circuit must be in this frequency, because that is where the reactance of the series circuit is inductive. But the important point here is, if you take any frequency of desired oscillation, the slope of this curve at this point is much higher than the slope of the curve for corresponding to inductor, simple inductor. Simple inductor will have a straight line depending upon the slope of this, which is the slope of this will be just equal to value of inductance, and here the slope varies and the slope will be much higher than this inductor slope. As a result of that, we can show, I will not go into that, but we can show that the frequency stability of this oscillator is much better than the corresponding Colpitts oscillator. So, whenever we have the variation around the oscillation frequency for a small change in omega naught, the changes a much larger value of this omega in x omega, then you will have a much higher frequency stability. That is the reason the Clap oscillator is used, because of this change in this incremental change in the reactance with respect to change in the frequency from the oscillation frequency being so high compared to an inductor. That is where the Clap oscillator has become. This is the time when people 1940s, people have discovered that if you take a piece of quartz crystal and cut a slice out of that quartz crystal and put it between 2 electrodes, then this mechanical system, which is a piezoelectric crystal, quartz is a piezoelectric crystal, has an equivalent electrical circuit which is like this. This piece of quartz put between two electrodes, two plates like a capacitor, and this one has an equivalent electrical circuit given by what I have written here. And the beauty of this quartz is, this is comparatively much less sensitive to variation in the temperature. So, all the frequencies of resonant frequencies associated with this network are very stable resonant frequencies even when the temperature changes. Now, if you see x omega for this, it has 1 0 corresponding to this, and it has a pole corresponding to this in series with these two capacitors. So, there is one parallel resonant frequency and one series resonant frequency. Okay. Now, since the series capacitor is always less than the capacitor by itself, so the 0 comes first and the pole comes next. So, we have a 0 here and a pole here. Are you with me or not, what I am saying? So, how does the variation look like now? The variation looks like this. And usually these two frequencies are quite close. Now, you can see for this x omega variation with respect to omega, the slope of this is much larger than the corresponding clap. So, this oscillator will have much higher frequency stability compared to the clap oscillator or the original Colpite oscillator. That is why the PS became a very popular structure using a crystal. And the frequency stability you can get in Pierce oscillator using a quartz crystal, depending upon of course the quartz crystal, but any commercial quartz crystal made for this purpose will give you frequency stability of the order of 10 in 10 to the power of 8 typically. So, you can get frequency stabilities of the order of 1 in 10 to the power of 8, and with some effort I can even push it to 1 in 10 to the power of 10. What it means is it loses or gains one cycle over 10 to the power of 8 cycles. So, this is the kind of oscillators which you use whenever you have a timing requirement. For example, in computer where you want all the timing signals will always come from a crystal oscillator sitting in the computer using a small crystal which will have a stability like 10 to the power of 8. And in this watch there is a crystal oscillator which will give the stability which is required for giving. So, people sell you clocks by saying it does not lose more than 1 second over a period of 10 years and 20 years and so on and so forth, which amount to a number like 1 in 10 to the power of 8 or 1 in 10 to the power of 10. So, that is the terrific advantage of the Pierce oscillator. So, you just take a quartz crystal and cut a slice of it, and the frequency of oscillation, the 0 and omega and the pole frequency depends upon the size of the piece you have cut out of this quartz. And it also has been found if you cut the quartz crystal in certain crystal axis in certain way, the frequency stability is even higher, and this cut is known as the AT cut. Don't tell me what, I don't know what this AT stands for. It is some angle with respect to the crystal axis, and that angle is called the AT angle. So, if you cut that quartz crystal in that particular angle and take a small slice of it, a rectangular piece, and then put it between two electrodes. You will get these two frequencies depend upon the size of the quartz piece. So, you can buy a quartz crystal for a resonant frequency from market and then put that into it and then make your oscillator.